So we were talking about 500 millibar maps and ridges and troughs, and I wanted to put the 3D map right next to the 1D map so you can get a better feel for those ridges and troughs. And what we have here is a trough in the 3D map, and I am putting this together with some cold air coming down from Canada. So there's an example of the plane at 500 millibars, where everything above the plane is at 500 millibars of pressure above you. And this trough that came out of cold air from Canada is shown on the one-dimensional map as a trough in the gray lines here. I want you to try to ignore the red lines. Those are actually temperature lines, and we know PV equals nRT. Temperature is going to follow along with pressure, but it's not exact, and we'll learn a little bit more about why. Follow the gray lines here for this trough. And this is the cold air coming down that's related to this. In addition, there is a ridge right nearby, and this is actually warm air coming up from the equator along the Pacific and producing higher altitudes for that 500 millibar plane along with that warm air that has risen and expanded. So I hope that helps you to understand a little bit more about that. And we just move this a little bit farther. There, next one, good. There's another way of looking at the troughs and ridges. There's another ridge there that right around Texas that's coming out of the Gulf of Mexico. If you're wondering how to make a 500 millibar map, you have a lot of the ingredients already in your soundings. So what people will do is they will take the soundings and take it all across the country, those 2,000 sites, and they will look for the altitude of the 500 millibar placement. Remember, the y-axis of the sounding is set for the pressures. So you see 1,000 millibars at the bottom, 750, 600 millibars, 500 millibars, 300 millibars. But the altitudes along the y-axis are not set. And so computers take all of those 2,000 soundings and record the altitudes for the 500 millibars and then just draw contour maps, much like isobar maps, by matching the contours that match for altitudes that are right within about 10 meters. So you usually have 10-meter maps. Sometimes you'll have 100-meter maps, and they will fit in all the altitudes that are between 5,100 and 5,000 meters and 4,900 meters, and all the altitudes will fit in between those gradients. In addition, sometimes those contour maps, when we make them up, can look like this. You can put colors in them, and they can have really tight gradients in here where we would expect to have higher speed winds at the 500 millibar level. And you can also have broader gradients, like here's a real broad gradient here where you'd have much gentler winds in the central United States at the 500 millibar level. Here's another example of a wintertime 500 millibar map, and you see the cold air producing the trough from Canada. Now this is what's important to sum up. We've gone over surface maps in the prior videos. That's everyone on one altitude because we corrected to create a horizontal plane at the surface. Go over that. You'll see different pressures at the surface so that we can make our pressure gradient forces going from high pressure to low pressure on those 4 millibar intervals. On the other hand, the upper level maps, everyone is at the same pressure with different altitudes for that pressure. So go over that and understand the difference between surface maps and upper level maps. They both have lines. The surface maps are isobars. The upper level maps are contour lines. And that's what I'm mentioning here. The surface maps are isobars. Those lines are drawn to link individual surface pressures in 4 millibar increments. And the upper level maps feature contour lines like topography lines, one set pressure with different altitudes for that pressure. Warm air, higher altitudes, cold air, lower altitudes. Hope that helps you out.